Hi, so it's evening for me. I don't know where everyone else is, if you're in the morning or the afternoon currently, but welcome to Python for Orbital Mechanics. My name is Husseina Etibalogun, but you can just call me Husseina. We're gonna hopefully spend the next 5 weekends together, the next 5 Saturdays. So I want to give a brief introduction to the motivation of this course. So, less than 9 months ago, I was a bachelor student studying mechanical engineering at the Federal University of Technology, Akure in Nigeria. And before graduating, I got the opportunity to get a master's in space systems engineering at Kyushu Institute of Technology here in Japan. So, of course, I took the opportunity and I came to Japan. So, in the first semester, there was an elective that I was really excited for called Advanced Space Dynamics. So, I was like, "Hey, I'm gonna start doing space things." I was happy, right? So then I took the course, and then after the semester ended, I I got my results and I got a B. A B isn't bad, but the immigrant in me saw that B and it started to look like a B minus, and then that B minus started to look like an F. So I decided that I want to relearn the course because I knew that I didn't really fully understand the course. So I wanted to relearn it, right? So that's why uh, I wanted to do this. But then I realized that if I was just running on my own motivation, I wouldn't do it. I don't really do things a lot when I'm only interested in helping myself. So I decided that okay, maybe I should teach some people. That would motivate me more to relearn the subject, because then I would actually have to teach people. So yeah, that's how we got here. So now I'm going to go through the contents for the next 5 weeks. So for the first week, which is this week, we're going to go through just a little very brief introduction. Then we're going to look over the two-body problem. Then in week 2, we're going to dive deeper into moving elliptical orbits, which we're going to briefly do this week, but week 2 will be like a more in-depth look at like the actual elements that make up an elliptical orbit. Then week 3, we'll look at coordinate systems and converting between coordinate systems. Week 4, we'll look at maneuvering a spacecraft that's like delta V, Hohmann transfer. Then the last week, we will go into the Lambert's problem. I don't think we'll be able to, not that we won't be able to, but I don't think we'll solve it. I just want to demonstrate some Python libraries for space applications that are currently in existence using the Lambert's problem. So we might not like fully solve the problem by the end of that week. Yeah. So let's start. Quick disclaimer, these classes are not for deriving equations. I will try to explain the equations as much as I can. I'll briefly explain them and then we'll use them within the code. And like I said before, this started off as me trying to make sure I really understand this subject. So if you have any questions, I will do my best to answer them. But please know that if I can't answer, I will just say I'll do some research and get back to you next week. So also, if I say something that sounds a bit iffy, please do let me know if you have any corrections. So yeah. So there's a whole history, right, that precedes the current state of orbital mechanics as we know it. And we don't have enough time to go through that. So I'm gonna start at the part that most interests us, which is the 1500s. Now at this point in the 1500s, and by we I mean astronomers, space enthusiasts, we knew that there was a difference between planets and stars, right? So we knew that there were these objects that were far, far away from us and they were moving in the sky. But we still thought that the sun was one of 7 planets. And everybody at that time was running on on the Platonic assumption that all celestial motion, including planetary motion, was circular and uniform. But the only problem with that is that they had already observed that planetary motion was not circular and was not uniform. So the major problem at the time was the Greek astronomical thinking. So they were very adamant on fitting observed facts to a presumed theory rather than developing a new theory to fit the facts that they had. So enter Danish nobleman, Tycho Brahe. So this guy was a nobleman. He was rich. He had money. And he was interested in space, right? So he used his money to devise the most precise instruments at the time before the invention of the telescope. So these instruments allowed him to more precisely detail the motion of the planets. And in particular, he compiled an extensive data on the planet Mars. So fast forward to Kepler, uh, Johannes Kepler, yeah. So he used Brahe's data, which is way more accurate now, in his formulation of the laws of planetary motion. He was able to demonstrate that the orbit of Mars was not circular, but it was an ellipse, and that the speed of the planets were not uniform, but that they followed his second law of planetary motion. So with his new laws, he was now able to correctly explain the varying speeds of planets that the Greeks and other astronomers had observed. So what were his laws? So Kepler's first law states that each planet orbit around the sun in an ellipse. So the sun's center is always located at one of the focuses of the orbital ellipse, and the sun is at one focus. So the planets follow the ellipse in an orbit, which means that the distance from the planet to the sun is constantly changing as it goes around this orbit. And this is normally represented by this equation. And the r is the distance from the planet to the sun, and p is something called the semilattice rectum. You can do some more research on that. I'm not going to go too deep into it. We'll just use the equations. Yeah, so that's Kepler's first law. So his second law is the law of areas. And it states that there is an imaginary line joining a planet and the sun, and that line sweeps equal areas of space during equal time intervals as the planet orbits. So let's say a planet goes from here to here, and this area is the same as the planet going from here to here. That's area 1 is equal to area 2. That means the time that it took for it to go from here to here is the same as the time it took to go from here to here. So that is normally visualized or represented by these equations. So then his third law was the law of periods. And sorry. So the law of periods establishes the relationship between a planet's orbital period and its distance from the sun. So it states that the square of the orbital period of the planet is directly proportional to the cube of the semi-major axis of the orbit. So from here to here is what we call the major axis, right, of an ellipse. So the half of that is what we call the semi-major axis, and from here to here is the minor axis. So these two sections individually would be the semi-minor axes. So this law basically says that the distance from the planet to the sun directly affects the time it takes to orbit. So this is explained in like Mercury. Mercury is the innermost planet, right, in our solar system, and it takes 88 days to orbit the sun. And the R from Mercury to the sun is far smaller than the radius from, let's say, Earth to the sun, because it takes the Earth 365 days to orbit the sun. And then we have Saturn that takes over 10,000 days to orbit the sun. So this has been proven. So Kepler worked out that the planets moved this way, right? So then after Kepler came Newton. So now that we have all this information about what came between before Newton and his, falling apple, directly from Kepler's third law is where Newton derived the 1/r² variation of the gravitational force with distance. So Kepler explained how the planets moved, and he knew that there was a force, some unknown force in the universe that was enabling these movements, but he didn't know what that was. So it was Newton that now discovered this force, and he called it the law of gravitation. So Newton now explained the planetary motion in terms of gravitational force. So like by Newton's second law of motion, he says the net force of a body is equal to the body's acceleration multiplied by its mass. So F is equal to ma. We all know that. Then he stated that every particle attracts every other particle in the universe with force directly proportional to the product of the masses and inversely proportional to the square of the distance between them. And we have this gravitational constant for our universe that was measured by Lemke, I think. I can't remember his name. But this was measured, and this is the value that we have, right? So with this equation now, we can now rewrite Kepler's third law as this. And this was, as I mentioned before, A is the semi-major axis. So this was now replaced by R, which is the same thing, like the radius between the planet and the sun, or the bigger body. So all my talking since morning has finally gotten us to the topic of today, which is the two-body problem. So the two-body problem is a set of assumptions, right, that helps us determine where a planet will be in the future. It helps us determine planetary orbits, right? And these are the assumptions. So we assume that the universe, sorry, can you please, okay. Okay. So we assume that the universe only contains one very large body and one small body. Then we assume that the large body is spherical and that the mass is evenly distributed, with the center of mass being at its geometric center. Then we assume that the large body influences the small body gravitationally with a force coming from its center, and the small body does not influence the large body. This is the assumption. Then we also assume that the reference frame is centered at the geometric center of the large body. So equating the two, the Newton's second law and his law of gravitation gives us this, right? So then we get, in order for us to predict or simulate an orbit, what we need is the acceleration. We need its movement with time, its speed per time, its velocity per time. So equating these two equations, we are able to get the acceleration as this. And this mu is a constant for everybody. So everybody has its own mu. So like the Earth has its own mu, the sun has its own mu, Saturn, all the planets have their own mu, which is the gravitational constant times its mass. So I want to also briefly talk about the n-body problem. So the n-body problem, the two-body problem is a type of n-body problem. And the n-body problem is just a problem that states that given a quasi-steady orbital property, given the quasi-steady orbital properties, that is the instantaneous position, velocity, and time of a group of celestial bodies, we want to predict their interactive forces and consequently predict their true orbital motion. So it's a problem of predicting individual motions of a group of celestial objects interacting with each other gravitationally. So the two-body problem is just a section of that. And then from there, we can have three-body problems, four-body problems, five-body problems. And as you know, the universe has many tens, thousands, millions, billions of bodies. So the three-body problem is a special case of the n-body problem. And unlike the two-body problem, which has been fully solved, there is no general closed form solution for the three-body problem. So we're not going to go into this in this class, but we're going to go into this in the coming weeks. So I want to explain it. So the sphere of influence is basically the volume around a body where its influence extends to gravitationally attract other bodies. So let's say we plan a trip, right? We plan a mission to Venus or something. If our spacecraft is on the trajectory to the planet to Venus, we don't want it to accidentally fall into the sphere of influence of, let's say, Mars on its way there. So we need to know how far the influence of some bodies extend so that we can plan our trajectories accordingly. So the general equation is normally described as the radius of the sphere of influence, and it's calculated using this formula. So that is the end of the explanation part, the theory part of today. I will move on to the coding now. Does anybody have any questions? Okay, if we don't have any questions, I'm seeing now it says we have about 7 minutes left on this. So can we end the call and start another one? Because I don't want it to cut off halfway as I'm doing the coding. Okay, cool. Let me stop this recording. Also this PowerPoint is available on the GitHub link that I put in the WhatsApp. So if you're interested in the sources that I used to do the research for this, these are the references at the end of the slides. Yeah, so I will end this call and then start a new one so that we don't get cut off later. It will be the same. I'll just end and then we can restart. Okay, when I restart the new one, I'll send the GitHub link to the chat. Is that good? Okay. Oh, I was on mute. Sorry. Thank you very much for telling me. Okay, so yeah, I've sent the GitHub link. And no, I'm not using Cosmographia to visualize. We are using Pygame. And I was saying that most of the code that we use will not be my code. It will be code that I scour from the internet and then just explain the concepts. So this particular code, we're not going to be doing 3D visualizations. We're going to be doing this is a 2D. This is going to be 2D visualization. And then from this code, you can also develop it to make a 3D visualization. But this is using Pygame. So if you go to the GitHub, there's an explanation of how to clone the repo. So once you go to your terminal, git clone, you will see this, open the folder, right? Go to your terminal, open the folder, and you will see this. So this is the standard library of classes and functions that we're going to use. There's a vector.py file, standard.io file, a standard draw file, which is what we're going to use to draw our bodies and our universe to the screen. This is standard array that we're going to use to create the arrays, the one-dimensional, two-dimensional, and then maybe three-dimensional in your free time. And then this instream.py file allows us to read from files. And then this color.py file allows us to change the colors of our objects. So the first thing we're going to do is go into code, because that's why we want to create our file. So just cd into code. And in the two-body problem, the first assumption is we have a universe, right? There's a universe, and in the universe, there only exists two bodies, a very large body and a very small body. So the first thing we're going to do is in the code folder, we're going to create a universe.py file, and we're just going to leave it empty for now because our universe is empty, right? The first thing after creating the universe is we need bodies. Okay, so then let's create another file called body. What is this here? Why is rename? Okay, body.py. Okay, so in this body.py file, we are going to create a body object that has the attributes of position, velocity, and mass. And this is not the file that we're going to run because we're going to run the universe.py file with this body object. So this is not going to have like a main function or anything. So let's create the class, right? And the first thing we want to do is initialize our body, right? And we say that the body has three properties, position, velocity, and mass. So we have position, R. You can just call it pos. Let me just call it R. Then we have velocity. Then we have mass. Okay. So I'm just going to leave this for now. Then what do we want our body to do? Our body should be able to move, right? So we're going to define another function called move. And it will be able to move only with force and time, right? We need to be able to know the force that is the force that is what do I want to say? Not attracting. The force that is affecting the body and the time that it's moving in. Okay. Then we want our body to be able to be gravitationally attracted to and from other bodies. Okay. Where do we create the body.py? Okay, so in the Pi for orbital mechanics folder, there's a code folder, right? There's two folders, code and resources. Oh, apologies. So there's code and resources. It's inside the code, there's a standard library. So it's in the code that we're actually going to create. I don't know why it didn't do that initially. I thought I was in the code folder already. So it's in the code folder that we're going to create these two files. I accidentally created it outside. Thank you for letting me know, Samuel. No, we can't create files inside files. So we're not creating body inside universe. We're creating two different files, universe.py and then body.py, because the universe is going to use this body file. Okay. Are we all up to date? Yeah, okay. So in the body.py file, we have the class body. We want to initialize the body. Then we want to create a function that allows the body to move. Then we want to create another function that allows the body to be gravitationally attracted to and gravitationally attracted from other bodies, right? So we're going to call this function force from. And then self. So there's a force coming from itself and then a force coming from other bodies, right? And then the body should be able to draw itself to standard draw. So this inside this standard library, there's this standard draw.py file, and this is what allows us to draw our objects to the screen. So we want to be able to draw this body to the screen. So we're going to define another function called draw. So we can draw cell to the screen. Okay. So these are all the things that we want to do with the body, right? So let's go back to the init function. We want to initialize this body. So this body we've said has 3 attributes: position, velocity, and mass. So we're going to assign these to itself. So self dot equals self dot underscore r equals r. So you can just do self dot r equals r, but this is just kind of like a standard way of saying that this hello? Please. Okay, you've muted yourself, thank you. This is just a standard way of saying that you shouldn't be able to really access this outside. You shouldn't be able to access this dot self variable outside of this scope. But it means the same thing as just saying self dot r, but we'll just put this. So this is the position, right? Then we'll assign velocity to v. Then we will assign the mass of the body. Do I still have to put that? Just for clarity. Yeah, this is the mass. Okay, so now in order for the body to move, we need the acceleration, right? And we have already stated that force equals mass times acceleration. So to get acceleration, we can just do A is equal to F divided by M. And now we have the mass. We state the mass of the body, right? So A is equal to the F that we state here. This is the force. Force. So the force is a vector, and there is a vector file here where we can take this vector class, and it has a function within the vector class called scale, which basically outputs a multiplication of the numeric value that the numeric object that we state, and then whatever attribute of self that we want to multiply it by. So f dot scale. Now we don't have to import this vector file into this because we're still going to import it in the universe. So like it will when we import it in the universe file, it will like automatically join with this. Like you don't have to import it into this particular file. So there's f dot scale, and then f acceleration equals force times mass, force divided by mass, sorry. So which is the same as saying force times 1 over mass. So we can say scale, f dot scale 1 over the mass of self that we have already stated. Okay. So then now that we have this acceleration, this is instantaneous acceleration, right? Like the acceleration is changing at every point. So the value of the velocity and the value of the position is also changing at every point. So acceleration is, we said F is equal to ma, right? But also acceleration is dv over dt. Are we up to date? So when we expand this, we can get A is equal to our v minus v naught, right? Over t. So then to get the instantaneous velocity, like the next velocity, we have the previous velocity plus a times t. We get v, our new velocity is equal to v naught plus a times t, right? So that's what we're going to, in order to calculate the new value of v, that's what we're going to do. So the new value of self dot v is equal to self dot v, which is the initial value, right? Plus a multiplied by dt, which is our change in time that we specify here. Okay. So the same thing, we can use that same logic to apply it to the position. So because position is equal to, the change in velocity is equal to, the instantaneous velocity is equal to change in position over time. So we can also do the same reverse engineering that we just did. Self dot r is equal to, the new value of self dot r is equal to the initial value of r plus v t, right? So now we have our acceleration and we have the change, we can change the value of the velocity and the radius according to the change in acceleration. Okay, so that's done. Now we want to return the force between the object self and another object. So this is where the bulk of the equation that we were talking about before comes in. To do this, this is F is equal to, G m1 m2 over r squared. So first we need to define the constant G, our gravitational constant, which is 6.67. And then the difference between the radius for ourself and the other body, we'll call it delta. That's the difference, right? So the r, the radius of the other planet or body minus our orbital radius. That's the delta. Then we take the absolute of this. That will be our distance. This is equal to absolute. Okay. Okay. So now our magnitude, which is our force. Is that how to spell magnitude? I think so. Yeah. It's equal to G times mass, gravitational constant times our mass times the mass of the other body all over the distance squared. The distance times itself, right? So this function is now going to return a value. And it's going to return the value of this force times the unit vector, which is the direction, the unit vector of this delta. So return. So direction is also another function within the vector.py file that helps you return a unit vector of an object. Okay. So now that we're done with this, we now move on to drawing ourselves to the screen. So we're going to use this standard draw.py file. And because we're going to within the universe.py file, we're going to draw the whole universe. We're not drawing the individual bodies in this. We have to draw the individual bodies in this file. So we're going to import the standard draw module. Sorry. So import. Okay. So inside this, there's a function that allows us to set the radius of our object, of our pen. So we're gonna put some pen radius here. And it needs to be less than 1. So just put 0.5. You can change it to whatever else you want. And then we're going to initialize the starting point, right? Draw. It's another function that takes in the x and the y values. So self, and that's our position, the initial position, and then x and the y. Okay. So now we're done with this body file. Now we can create a universe using this body file. So our body now has 3 attributes. It can move according to the acceleration that we've calculated. So we can each new value of the velocity and the position are changing based on the acceleration, and then it is being gravitationally attracted by other bodies and returning this the function of mu over r cubed times the unit vector. And then we can draw the body to the screen. Okay, so now let's go to our universe.py file. Does anybody have any questions? Okay. Okay. So we're going to create a class called universe. Now, this file is what we want to run. So this file needs a main function. And this is just like a bunch of syntax that is needed. If main. Okay. So this file, we want to run this file in accordance with another file. So we're going to have an external file, a txt file, that has the values of like our starting point values. So it's going to have the number of bodies that we want to run in our simulation. It's going to have the magnitude of the force, the value of the force. Then it's going to have the initial position, the XY position, and the XY velocity values. And then it's going to have the radius of those bodies. So we want to read from the command line, right? So we want to read a file name from the command line. So we need to state where that file is coming from. So arg b. Because let's say this is how we want to run it, right? So we want to do like Python 3, then universe.py. Then we want to run our file, let's say 2body. See? Then we state the time that we want to run it for. Let's say 20,000 seconds or 200,000 seconds. So this is how we want to run the file. So this is the first command, right? On the line. Then this is the zeroth command, right? This is the 0th argument. Then this is the first argument, then this is the second argument. So this is the argument that we're reading the file name from, right? And then we're going to be reading the values from this. And then we're going to be reading the time from this. So that's how we want to run the file. So the t, that's the time. We're going to run it as a float. This. Oh, I'm doing all of this and I forgot to import. Okay. 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 Go down. Let's put this all the way down here for now. So now, this should be within this class. Yeah. So now I want to initialize this class. What is in this class? What attributes does it have? Well, it has itself, and then it has the file that we want to run from the file that we want to read the values from, right? So in the standard library, there is a instream.py file, and this helps us read values. It helps us read ints, booleans, strings, floats from whatever the file is. So we're going to import. Oh. Yeah, so we want to import this class from this file. Yeah. So that class is going to help us read this file, whatever the file is that we read in our command line. Then the first thing in that file is going to be the number of bodies that we want to run in the simulation, right? So let's assign that to n. N is the number of bodies, and we're going to use the read integer function within instream. Read int. Okay. Right. Then the next value in the file, in our txt file, is the radius. The radius from our planet to the radius of the one body to another body. So let's assign it to this value. And it's going to be a float. So we're going to read the float. Read float. It seems I might have to not use Zoom because it keeps telling me that it keeps giving me time constraints. So now it says 9 minutes left, 9 minutes, 40 seconds left. So what do you suggest we do? Cancel a start again, or let me just finish this function first. So we assign the radius to the value in the txt file, and it's going to be a float. So yes. Then we need to set the scale of our pop-up box. So when we draw this universe, it needs to be on the screen, right? So we need to set the scale of the screen. So in the standard draw, let's import standard draw. So in the standard draw module, there is a function called setXscale, and we're going to just use the radius, the plus and y values of the radius, not the plus and y, sorry, the negative and the positive values, so that we can make sure that our screen is wide enough. It will definitely fit our simulation. So stddraw.setXscale. So we're going to set the x scale and the y scale. You shouldn't really do that, but I just did. Then we're going to create an array of bodies based on the number of bodies that we put in the file. So let's say this is 4 bodies that was in the file. We want to create an array of bodies of all the bodies that we have, right? So let's create an array of bodies using the standard array module. So I'm gonna have to import that. Using the function create 1D. So we're going to create a one-dimensional array that is the size of how many bodies we have. Then for every body in that array, we're going to assign the position, the x and y position, and the x and y velocity values, right? So for I in n, that's the number of bodies that we have. So we're going to read these values from the file, right? Stream. Dot, these are floats. No, I really shouldn't do this, but so now we're going to read these floats from the file. So our x position, y position, x velocity, y velocity. Okay. Then we're also going to read the value of the mass from the file. So now that we've read these values, these initializing values, we're going to put them in a vector using the vector module that is already in our standard library that I have not imported. So from glib.vector import. So we're going to create an array for a vector array for the position and a vector array for the velocity. Okay, now are we all good? Okay, no questions. So now that we have initialized this vector array, our position vector and our velocity vector with these values, we now want to put it in the body, right? So for I in the range n, that's the number of bodies that we have. We want to assign these vector values, right? So we want to create body objects with these values for each body that we have did. Okay, so that we have initialized our universe to have a certain number of bodies with these values, with these vector values. Okay. I need suggestions of what to do because there's 3 minutes left on the clock and we still have quite a ways to go. So should we restart again?
Yeah, I think we should restart again. Then you can merge the recordings.
Okay. Okay. Okay, I'm going to stop the recording now. Stop. I refuse to believe that 2 14-minute sessions have already passed by. I don't know. So yeah, where were we? I'm gonna save this because even though my laptop won't die, I have PTSD from my laptop just randomly dying on me. So please save your files. Don't forget to save your files. Okay, so we have initialized our universe. Now we want to simulate the passing. So what other functions does the universe need, right? That's what we should ask ourselves. What does the universe do, right? What can we put in functions that the universe can do? Well, the universe is going to... Wait, somebody wants to answer my question? No? Muted. Yeah, so what is the universe going to do? Well, time passes in the universe, right? So we want to simulate the passing of the time. So we're going to create a function called increase time. Increase time. And that function is going to have a value that we're going to specify in our command line. That last value that I showed you, that like 2,000, 10,000, 3,500, that's our change in time. That's how long, that's how much time passes, right? So this increase time function is going to have this this value passing into it. Then what else does the universe do? Well, the universe is going to have to be drawn to the screen, right? So we're going to also create a draw function. And it's just going to draw itself, right? Okay, so let's go back to our increase time function. So the first thing we want to do is we want to know how many bodies are in our universe. So that we know, like, what is being affected by what. N is equal to, we're going to count, I don't know why we need to even count this, but we're going to count the bodies that we've initialized. How many bodies have we initialized in our universe? And assign it to the value F. Okay, so what we're doing with this is we're going to use this to initialize the forces to zero. So however bodies that we however many bodies that we have, right? They're going to affect each other within this time. So we first want to have their forces initialized to zero before it moves up to the force defined in our txt files. I don't know why I created that. Okay, so then we're going to have our force, and our force is going to be a vector array that we're going to initialize to zero. So we're going to borrow again from this standard array module and create a one-dimensional array with the number of bodies that we have, a vector array initialized to zero. Okay, so our force is zero. This is the number of bodies that we have. So now we want to compute the forces. Okay, so for every body, it has a force to another body, right? So we want to create a for loop in another for loop for this. So for I in range, the number of bodies that we have, then for J in range, number of bodies that we have. If our first body is not equal to the second body, we want to have, if this how do I explain this? If this value of the force vector is not equal to this one, then we want to put this inside our first body. So we're creating the force vector, but we're creating we're assigning the forces to each body. Please let me know if you don't understand. Elijah, yes. Can you show me again the libraries we are importing? Okay, so on the side here, there's a standard library folder. This is where all the files are. So this is the library that we're importing. That's why we're doing this dot notation importing. So from this folder, we're importing this file as this. So we're importing standard array, standard draw, in-stream, and vector. So vector helps us assign the values into a vector. In-stream allows us to read read data from the files. And then standard array helps us create arrays, one-dimensional arrays, two-dimensional arrays. And then standard draw helps us draw our simulation to the screen. So yes, that's it, Samuel. And then Elijah, yes, this will be uploaded to YouTube. So I'll merge them, try to upload them maybe this weekend or maybe my Monday or Wednesday or something. And yes. Yeah, so if I is not equal to J, right? We want to create. Do you have a question? Do you have a question? No? Muted. It gives me joy to mute people. I don't know. Is that a bad thing? So if I is not equal to J, we're going to have a body, our ith body. I'm going to assign it this value in bodies, right? the values in. Then we're gonna have our J body, our second body. Why are you not allowing me to do that? So now we're going to have the force, our instantaneous force. The force of I is equal to the instantaneous force of I is equal to the initial force value that we have for I times uh the force that we're getting from the second body. So the force, the instantaneous value of the force is our initial value of force plus the force that we're getting from the second body. So body I, these values, this function that we just created in the body.py file, right? This is a force from our body J. And this is with the assumption that our ith body is the largest body, right? Right? Yeah, right? No, the force is coming from J, so J is the larger body. Please don't be confused like me. Don't let me confuse you, sorry. So now after we have we've initialized the force to zero, the forces to zero, then we've computed the forces. Now we want to move the bodies, right? So why do I keep doing that? For I and range number of bodies that we have, we're just going to use a move function that we put in the body.py file, right? Because using that move function, we calculated the acceleration and then we changed the instantaneous values of our position and our velocity. And that's already in the body.py file, so we're just going to use that function. Move. Here we said that we want to put in the value of the force and the time, right? The time difference. So this is our F, our force vector that we've created that we initialize to zero, and then it's going to be constantly changing for every value, right? So F of I, comma, dt. So now that we have initialized our forces to zero, computed the forces, and moved the bodies, like we can now move the bodies, we can move on to the draw function. So for every body in our self.bodies array, the number of bodies that we have, we just want to draw the body. And so we'll just use the body.draw function that we created here. For bodies. Okay. Okay. So we've initialized our universe. we have enabled it to increase with time. So have the force change, and then the body moves with the force and then draw itself to the screen, right? So let's go back to our main function. Why did I bring it all the way down here? Run the file. Control S. Save your files, you guys. I'm more scared for your files than you are. Okay. So in this main function, now we want to actually say what we want the file to do when we run the file, right? So we're going to have a universe variable that is going to use, we stated here that our universe class takes a file, right? So we already stated that our file is coming from the zero, the first argument in our command line, not the zeroth, the first. So use the universe class and take file name, not equals, just file name. And then while true, because we just want this to run, while true, run this function, universe dot increase time with dt. Then standard draw, create a plane output, draw our universe, and then show us our universe, right? So save this. Okay. So I was talking earlier about the txt file that we wanted to run. Why is it giving me two warnings? Oh, did I forget to import body? Yes, I did. So please do not forget, like me. Body import. I want to import this function. Okay. So one is gone. I have another one left. Oh, my bad. Sorry. Okay, I'm all good now. Everything's green. Okay. So now we actually need the values that we want to be reading from, right? So let's create another file, but this file will be, I don't want to create in standard library. I want to create it in code. So I'm in the code folder, create. This is our, let's say, two body. I want to read from this txt file. So the first line is how many bodies that we have, two bodies, right? The next line is the force, right? So let's say 5 to the power of. Yep. Then we're going to have 5 values here. The Rx, Ry, Vx, Vy, and then our mass, right? And this will be duplicated for however many bodies that we have. Because if we put, let's say if we put 3 bodies here and we only have 2 of these like this, let's say, it will run an error because it'll be like, hey, I'm expecting information for 3 different bodies, but you only gave me 2. So yes, let's state these values. So we're gonna start this one on 0. Ry, let's say 5 e to the power of 10. Then our velocity, initial velocity, for the x value, and then for the y value, and then our mass for this body. Is very big mass. I'm just gonna take the negatives of some of these. So this one will be the opposite. Yeah. And we're just gonna have them be the same size. Just to run this. You can change the values later. So now that we have our two-body file with the variables, the initial variables, we have our body, we have imported the body, we can create our universe. Let's try to run the code. So Python 3 universe.py. Then we're taking information from our two-body.txt file. And then we want to run it for, let's say, 20,000 seconds. So entity. Okay, let's try to run this. Ooh, universe.py.
सारी कंपनी सेलमैन है मेहर सिंह कोडूटा ही पहले हमें कुछ
Okay, thank you for muting yourself. Oh, so ready. Um, yes, why am I having a problem here? Why am I having a problem here? Hmm. The universe is not defined. Why is it not defined? Oh, because I put it inside this function when I wasn't supposed to. This is supposed to be outside of the function. Because this is inside this line if I put it here, right? Yeah. Okay, let's try and run it again. Hmm. So I have the draw comes up, the screen comes up, but my bodies are not showing on the screen. Is anybody trying to run this right now? Mm, mm. Why am I having this issue? Everything looks good. So is anybody running this currently? I want to check something. I want to check if it's because I'm trying to share it that it's not showing. I'm trying to run it again. Hmm. Is there a problem with this file? Oh, maybe this is too small. Maybe my false value is too small. Let me check. Hmm. Oh, what's this? No budget. Select language, fill template, or open a different editor to get started. Start typing or dismiss. What are you running it on, Samuel? Line 17 in STD draw. Oh, I think I solved this before. That's change the text. Okay. I want to be able to. I can't really do. Maybe it didn't save. No, it's saved. It's saved. If it wasn't saved, it would have like a black dot next to it. Oh, these kinds of coding problems. So I have another. Let me close this. I have another file that I was practicing with before this class. I want to make sure that I didn't do something wrong in there. Um, this error is from what? Standard library color. No, it's from draw. Oh, so why oh why? I'm just getting a blank screen on here on my draw. Okay, let me stop sharing and see if let me stop sharing. Give me a second, please. Is anybody else apart from Samuel running this? Oh, I feel bad. Unfortunately, I don't think I can show you this. I wanted to show you how it's supposed to look. Okay. As I am unable to figure out what the heck I did wrong. Um, hmm. What I will do is, because I don't want to waste your time, I will figure it out and then push the correct code to the repo. Yes, to the repo. But in the meantime, I want to show the assignment that I put and the assignments that I let me show this again. The assignments that I'm talking about, they're not absolutely necessary. You don't have to do them. But if you check in the references of the if you check in the references of the the PDF that I uploaded, you will see where the website that I got this code from. So if you're interested more in like the details of like how they created these files, you can go into it will be the I think it's the Princeton website or something. So I want to quickly show the assignments that you can also check out. Uh New share. Okay, so there's three options that I put. So the more easier one would just be to create your own TXT file to simulate the n-body problem. Again, apologies for not being able to show you what the two-body one looks like. It was working, and that's how it always is. It was working before. Um, but yeah, just create your own TXT files to be read for other numbers of bodies problems. Then the next one is to develop a data file, the same kind of TXT file, to simulate the motion of planets in our solar system around the sun. So not just like two bodies, but the how many planets in our solar system? Seven. Around the sun. And then the harder one, I guess, would be to create a data type, universe 3D, to model the three-dimensional universe. Because what we modeled is to actually, yeah, I won't say two-dimensional, technically is one-dimensional because we created one-dimensional arrays. Which previous knowledge do we need to have for this course? Basic Python, like object-oriented programming, um and then like basics of Newton mechanics. The things that I explained at the beginning, which were like the laws of motion, law of gravitation. There isn't a lot of like super just basic things that we learned in physics, those kind of things. Laws of like how motion works and movement and stuff like that. So that's the basics that somebody should have before joining this. So yeah, if somebody doesn't know how to code in Python at all, then I wouldn't recommend this. And if you didn't do, I don't know, elementary physics also, um, brush up on it before you join again, I guess. So yeah, that's the end of this first class. I hope you, I don't know, not enjoyed, but I hope you gained something. And I will see you guys next week, hopefully. Does anybody have any questions? Any other
Oh yeah,
questions?
I have a question.
Okay.
Okay, first of all, I really enjoyed it. And I really liked how you started this from the very beginning.
Thank you very much.
So my question was that in the start you said that in the three-body problem we don't have general closed form solutions. So what does that mean?
What do you mean? Oh, closed form solutions. Okay, so like the three-body problem is like it hasn't been solved like outrightly. That's what I mean. That like there is no absolute solution for the three-body problem. That's what I mean by there are no closed form solutions in that. Like there are still so many uh types, so many I don't want to say deviations. So many, is it types I want to say? I don't know. Like there's so many solutions that it doesn't have a specific solution is what I'm saying. Like if you check out in the references, there's a website to the Wikipedia of the n-body problem and then the three-body problem. If you check out that site, you'll see there's a picture that has the simulations for the three-body problem, and there's just so many different types that there's no one solution to it. That's what it means, that there's no closed form solution. There's no absolute solution to the three-body problem. Well, for the two-body problem, there's
Oh,
no
I
absolute
get it.
solution.
I get it. So there's not one best way to go from one
Yes,
body to
yes,
another. Oh, okay, got it. Got it. Thank you.
yeah. Does anybody else have any questions? Okay, if nobody has any more questions, then thank you very much for joining, and I hope to see you next week.